Okay, thank you very much. I hope everyone can hear me well. I will tell you something about the capabilities to calculate NMR parameters and simulate NMR spectra. My slides are advancing fine. Can somebody give me feedback?
Looks good to me.
Yeah, all is good.
Thanks. Great. Okay, so NMR spectra carry a wealth of information. We can see this here, for example, this two-dimensional spectrum, correlated spectrum, where we get a lot of information in the form of chemical shieldings and spin-spin coupling constants. And while they are very sensitive and specific to a structure, they are only indirect structural information. So we, in principle, need a missing link between the molecular structure and the NMR parameters. And this missing link can be theory. So you can actually take a molecular structure, XYZ coordinates, feed it into something like ORCA and obtain an NMR spectrum, and learn a lot about what the experimentalists observe in their experiments. So how do we calculate chemical shieldings? If you look at this, the chemical shielding is dependent on the nuclear magnetic moment and an external magnetic field. And what's actually happening is that the electrons around the nucleus, they shield the nucleus from the magnetic field, and hence for every different nucleus, although they are, for example, all protons or carbons, you will see different signals. And so it's very sensitive to the electronic structure. And there's this early Ramsay's expression in which you see that you have a contribution from the derivative of the Hamiltonian with respect to these parameters, and with the response of the density. And these are called diamagnetic and paramagnetic terms, and they constitute the shielding tensor. So when we calculate this, we do this as a second derivative, and Frank Neser already mentioned that ORCA has broad capabilities of computing second derivatives, and this is how the final expressions looks like. And the important thing is, you don't need to know and understand much about this theory, but let me give you like 2 or 3 small insights about what the consequences for somebody who calculates these properties are. So if we formulate the Hamiltonian, you see that there are terms that occur which have high powers over 1 over r. So you have 1 over r cubed, and you have expressions that in some instances also carry the vector potential. So you have derivative with respect to the nuclear magnetic moments and with respect to the magnetic field. So for every nucleus, you in principle have 3 perturbations. If you do the calculation, that actually means that calculating NMR chemical shifts for all nuclei in the molecule will roughly be as expensive as, for example, calculating a Hessian. So if you can do a frequency calculation, you will also be able to do NMR shielding calculations. So a few things to be noted. If you include a magnetic field in the Hamiltonian to compute the chemical shifts, you have this vector potential. And on the one hand, this carries the so-called gauge origin, which is just a mathematical description of the field. And you have terms with high power of 1 over r. And this means, on the one hand, in finite basis sets, I will not go into details here, the results are gauge origin dependent. It's just you can call it a mathematical artifact of how you formulate the theory, and it has a dependence of high powers of 1 over r. So these operators that we're including in the Hamiltonian might have different behavior for the use of functional, the use of basis sets and parameters that you choose. You have to be aware of this. And as you're calculating this at a geometry, but for example, if you're calculating IR frequencies, your frequency calculation has to be done at the minimum of the potential energy surface. For chemical shifts, this doesn't have to be true. You can calculate the NMR chemical shifts at any point. That means if you have for example, geometry minimum at B3 lib level of theory, you can use any other functional to calculate the chemical shift. So you can pick and choose functionals that might work much better for chemical shifts, and other functionals might be good for geometries. And I will show you some examples. Now, I mentioned this gauge origin dependence, and the solution is called gauge including atomic orbitals, and this is default in ORCA. You don't need to be need to care about this, but you should be aware about this, or should be aware of this, because if you don't use a specific machinery for calculating chemical shifts, your basis set convergence will be very, very slow. So this is a typical example where you calculate, I think, proton chemical shifts for hydrogen fluoride. And even if you go to very, very large basis sets, you still have very large deviations. If you use these GIOs, then small basis sets will already be basically give you converged results. So this is default in ORCA. Any NMR calculation that you do in ORCA will actually use GIOs unless you specifically ask for other gauge origins. So what do? You calculate the energy if you do an NMR calculation, so you do the SCF, then the code will calculate the integral derivatives already using GIOs, and then you calculate from the unperturbed density the diamagnetic contribution, you solve the CPSDF equations, then you solve them for the 3 perturbations for every nucleus, and then you get the paramagnetic contribution and can calculate the full isotropic shielding tensor. If you do the ORCA tutorial and run one of these calculations, just for once, not only look at the chemical shifts that come out, but just scroll through the output bit by bit and try whether you can spot the different parts where ORCA is computing these different steps. It's really helpful because if you might have convergence problems or something goes wrong, it's much easier to point at what's happening if you learn how to read the output. Okay. For an NMR spectrum, in addition to the chemical shielding, we also need the spin-spin coupling constants. And just as for the chemical shieldings, where we need to introduce the magnetic moment and the magnetic field into the Hamiltonian, here we need to put the nuclear spins into the Hamiltonian and the electron spins that couple them. Because if you talk to NMR spectroscopists who measure shieldings or spin-spin coupling constants, spectra in solution, they will always call this indirect spin-spin coupling constants, because the direct couplings actually average out in a molecule that tumbles in solution or in the gas phase. And actually, this is not just one property, but we have actually 4 terms, so you need to solve 4 problems. And if you calculate the spin-spin coupling constants, you will see that actually you get these 4 contributions, and then out of these as the sum, you get the total spin-spin coupling constants. However, it's just one keyword that will give all the results that you need. So let's look at a typical example. And before that, just sum up. Magnetic properties are a little bit different from energies and frequencies, so you might have to use different basis set, different functionals. Gauge origin problem is already solved by using GIOs. But we've seen these high powers over 1 over R, so we need to describe the core region very well. So if you have heavy elements that use ECPs, calculating NMR properties with ECPs is not advisable. Use an all-electron basis set, so your electron density close to the nucleus is okay. Basis set and method dependence might be a little bit different. And if you want to be calculating full spectra, the coupling constants are also there in ORCA, so we have all ingredients. So I went to the literature. I just did a very broad search and looked for some benchmarks, and these are things that also Georgi Stoichev has been doing. Because the first question that we need to answer is, if we do these calculations, how accurate are the results? And here we see, for example, carbon-13 shieldings and proton shieldings for different functionals. And you can see typically for carbon-13, we get errors of 10 to 20 ppm, for hydrogen 1 to 2 ppm. So the spectral range for different nuclei is different. And I always highly recommend to look at the literature for benchmarks so you get a feeling for how accurate different methods are. And we see here, for example, B3-LIP, which is great for geometries, doesn't seem to perform that well. For shieldings, TPSS is a little bit better. And if we go to correlated methods, these are older benchmarks that we've done. You see that, for example, CCSD parentheses T, the gold standard for energies, is also very good for NMR shifts. And MP2 and DFT are roughly both in the same ballpark. So now basis set, we can see there is a specific hierarchy of basis sets called the PCS-SEC basis sets by Jensen et al. And these are basis sets which are specifically optimized for chemical shieldings. And there is also PCJ basis set specifically optimized for spin-spin coupling constants. So use these basis sets in conjunction with your functional of choice. And here we see we have errors of a few percent. So the basis set error at the PCSSEC3 level of theory, for example, or basis set level. So a specific triple zeta basis set for shieldings has fairly accurate results, which is these are much better, or the error, the remaining basis set error is much smaller than the functional error, for example, if you use DFT. Okay, so magnetic properties need special basis sets oh, this is duplicate special basis sets. We can use these to get robust and reliable results. Now for an example. So I found this example in the literature by Patil. This is actually a molecule that has been isolated out of a mixture of natural compounds and has been characterized by NMR. And we will just use this in order to see whether we can replicate the experimental NMR shifts by doing ORCA calculation. First of all, we do a geometry optimization, and I use B3LibD4 with a small basis set in order to get this. And then in order to have an idea of how accurate our results are with respect to the basis sets size, we try a few different basis sets, and then we do the same thing and do this for the different functionals. And an idea is to calculate the observed relative chemical shifts with respect to TMS. So we always calculate TMS as well as standard, and then subtract the absolute shielding of TMS from the calculated ones. And this is how we can match the experimental spectrum. So geometry optimization, nothing fancy. This is just a sample input. And what we get here is first geometry, and I call this geometry.xyz. And then we do the shielding calculation. I do this with TPSS. Benchmarks tell us this is quite okay. And then you just need a keyword, simple keyword NMR, and it will do the calculation for us. We'll try out different basis sets and functionals. So shielding calculation looks very much the same. If we want to be fancy, we can also use a compound script. So the compound script is a powerful framework to orchestrate calculations, and this is what a compound script would look like. You still give the geometry, but here you actually define a variable where you give all your functionals, and this is your ORCA input line. And what this does is it loops through all functionals and does 3 calculations in one shot. And the output file contains compound job 1 with B3lib, compound job 2 with TPSS, and 3 with TPSSH, for example. So this is really nice, and it makes your life a lot easier if you do series of calculations. What are the results? First of all, let's look at the basis set convergence. This is all with TPSS. And if I look at the carbon chemical shifts, what we see is that going from PCSSEC2 to PCSSEC4, the results only change by less than 1 ppm. And this is really nice. It shows us that if we look at the PCSSEC2 basis set, we will likely not be off by more than 1 ppm. So this gives us a lot of confidence in using PCSSEC2. Now let's look at the results. So these are the experimental chemical shifts, which I took from the paper of Patil. And here are the results obtained at the PBE level of theory. So we computed the absolute shieldings of TMS as a reference, and then we used this reference to shift these signals. And you can see that, for example, the methyl group comes out really nice at 20-30 ppm. The two carbons in this quinone residue 1 and 4 come out here. We have number 3, which is, this is a chlorine here in this case, comes out here, and the amine functionality, the carbon, also comes out here. But if you look closely, the assignment of these 2 atoms, 1 and 4, seems to be switched around in the theory, and also everything is like shifted to higher delta values. So let's go to a different functional, and let's look at TPSS. We see it spreads out a little bit more. We have 5 and 8 here, and 9 and 7 bracketing 10 and 6 is not in the theory, in the prediction here. So this leaves a little bit to be desired. The accuracy is not great. Even if we go to MP2, we see that the match is not perfect. And this brings us to the idea of thinking about our results. Maybe we can use a better level of theory for the geometry. We can use a better level of theory for the chemical shifts. What about solvation and maybe other structures might be important. So when you have these discrepancies, always sit down together with the experimentalist and talk about what the reasons will be here. I would put my money probably on electron correlation. I've often seen that MP2 is not sufficient and will switch around results. So that would be something to consider. If you want to calculate very quickly a full spectrum, you need the spin-spin coupling constants. And what we need is an additional calculation. I've chosen this example here. What we get is with a PBE and a PCJ basis set. So as I mentioned before, we use a different basis set. With these commands, we get all spin-spin coupling constants between different hydrogen atoms. And if we do this, we just can use either, for example, Chimera X, which has their own capabilities of reading the ORCA output, and then you can already simulate the spectrum, or you use ORCA NMR Spectrum, which is a post-processing tool where you can specify like the spectrometer frequencies, and you can specify NMR equivalent nuclei, and all of this is also documented in the ORCA manual. You just need to put in the GBW file and this input file here. And then in the end, voila, you get the simulated spectrum. And here you can see we actually have a much nicer agreement than we've seen before. The NMR experiments doesn't resolve the difference in these protons here, while the simulated spectrum gives us this. So in principle, we have everything here to get shifts and couplings, and if we combine all of this, we can easily simulate the full spectrum, and we can use compound scripts, and yeah, whatever the experimentalists give you, you have the opportunity to work on this in ORCA and to provide values that you computed to match structures and spectra. With this, I'm at the end. Thanks to Georgi Starchev for helping me along with tips and examples, and the whole ORCA developers team.